Okay then, so this week we're going to be talking about quantifying contextuality. In particular, so last week we made the distinction between models that were non-contextual. So we had the non-contextual models. But then we also had this notion of strongly contextual models. And in some sense, we would like to be able to think of these as being two ends of some spectrum. So you might want to assign a number, a quantifier, to the amount of contextuality, saying, okay, now maybe something that's non-contextual is 0, and something that's strongly contextual is perhaps some maximum number. And then it's also possible, because last week we also talked about how a given empirical model can be written often as maybe the convex combination of a non-contextual one plus 1 minus some p strongly contextual. And we might like to say that this thing, depending on the value of lambda, is somewhere between 0 and 1, and give a precise sort of quantifier to the amount of contextuality in this thing. And in some cases, like we'll talk about later on in the semester, we will want to maybe pin an operational interpretation to a number like this. So that's what we're going to be talking about in this lecture. We're going to quantify contextuality using something called the contextuality fraction. So we can always write an empirical model in this way, and we are going to define, so for a given empirical model P, we're going to define first the non-contextual fraction of an empirical model P as being the max lambda over, and I'll just write this sort of informally, over all decompositions of this form, P equals lambda P and C plus 1 minus lambda P. And by contrast, the contextual fraction will be equal to 1 minus the non-contextual fraction. So I wrote this a little bit informally, and you can actually make that a little bit more precise in terms of a certain kind of optimization program, optimization problem called a linear program. Got my P's mixed up. Okay, so in order to do that, let's just recall a couple of things. So we recall that we have a measurement scenario with a set of measurements, outcomes, and a set of subsets, the contexts, the maximal contexts. And let's define n to be the number of events in our scenario. So these are the number of outcomes, C to O, for each context C. So, and we define n to be the number of these things. We also define M to be the number of global outcome assignments. And we want to think of an empirical model P, an empirical model, as corresponding to some VP, which lives in R, let's see, Rn. Because I want to sort of embed this empirical model is a collection of probability distributions that are compatible, that agree on their marginals. And I am just sort of thinking this as the most basic representation you can think of. You flatten this thing out by just picking an order on your context and pick an order on your on your outcomes. And you just think of this as a real vector over the total number of events in your measurement scenario. We will in general say for empirical models Q and P, we say that Q is less than or P if and only if VQ is less than or equal to VP. And what do I mean by this? This is, I'm comparing the vectors. These vectors, in fact, because these vectors are of probabilities, all the entries in here are between 0 and 1. So I'm really comparing them element-wise. So I say that VQ is less than VP if every element of Q is less than an element of P. So we'll just need to remember that notation in a second, because we will use it in the definition of our linear program, the optimization problem that will give us this guy. So recall that we had this matrix M that we defined, whose columns were precisely the deterministic empirical models corresponding to a global outcome assignment. So we take its, each one labels a column. So we said we had M of them. So there's M columns here. And we said that an empirical model P is classical or non-contextual if and only if there exists a vector D. There's a D in Rm such that MD equals to VP, where D is element-wise greater than or equal to 0. Okay, why are we recalling this? Because in our definition of the non-contextual fraction, we're going to be relaxing this. We just want something that's going to be less than or equal to VP. Sort of the heuristic, or maybe an informal sort of intuition, is we want to capture how much of our empirical model can we capture using just non-contextual stuff. So how can we relax this thing? Well, we can relax it in the following way. The NCF using, so we have what's called a linear program using, or maybe we write it like this, via the solution to a linear optimization Now, it's going to look very much like this. Here, we only care about existence. Here, we're going to look for something that's optimal, and we'll see that there's an important difference. So what we want is to maximize a linear objective function, 1 transpose. This 1 is in R to the m, b, where b1 are in Rm, subject to, we want m times b, the same m times b less than or equal to Vp, and b greater than or equal to 0. So a couple of remarks here. I mean, this less than or equal to is well defined because we know that, so this thing, B in general, will not be normalized. If this was set equal to Vp, you would have normalization. This thing is not normalized. However, this thing is a valid non-contextual model once you divide by this value, which is precisely lambda. This is precisely lambda. So this is up to an overall factor, precisely saying that there is some non-contextual model which is less than or equal to Vp. So a couple of things to say about this. One is just that, the optimum of this thing, so if this thing is the optimum, it is the solution, the maximum to this, then we just say that this thing is, as I was saying, is equal to non-contextual fraction of P. Okay. It's worth pointing out that in order for a B to be feasible, so I mean, we are optimizing over all possible vectors B. They are not necessarily normalized, they're subnormalized. We're maximizing over these. And so which B's are valid? Which B's are what they call feasible? Well, the B's that are feasible are precisely the ones that satisfy this and are non-negative. And the thing is, you can always lower bound this thing by finding an optimal decomposition. So, if I know something about the supports, so I'll just give a quick example. I mean, if I know something about, for example, in one of these models, I know that there's something in the support, and I know the weight, the minimum weight of that support. So I think we discussed this last time. So then I can write, say, P is equal to some epsilon times delta, sorry, not delta, different notation, times dg. G is in the support, and then I just have some leftover piece. 1 minus epsilon p prime, say. This epsilon And we can give an example. For example, in the Bell model, which is the one that I'm thinking of, you can take out a 1/8 for one of these deterministic, for one of these supports. You can take out the 1/8, and then you've lower bounded this. You know that there's at least 1/8 on the non-contextual part. You know that it's not strongly contextual. So without actually solving the full optimization, you can still lower bound it if you know something about that empirical model. So that's another comment that I wanted to make. Of course, maybe it's not obvious, but if B transpose, other way around, 1 transpose B is equal to 1 as a integer, then it means that MB equals VP, and that this is classical. So we know that the non-contextual fraction is upper bounded by 1, which means that the contextual fraction is lower bounded by 0. And the third thing is maybe not so much technical, but more getting aligned with maybe what is a good heuristic for thinking about this, or an intuition. I mean, a natural question is to ask whether this thing is like a distance. Can I think of this as being maybe like the minimum distance from the non-contextual polytope? So we're not strictly speaking minimizing a distance. So to say that is maybe technically wrong, but I think morally speaking, it's okay. And maybe the better way to think about it is for the optimal decomposition, we have P equals non-contextual fraction of P, and C plus, and maybe I'll just make my life easier, contextual fraction times the strongly contextual part. Then I'm going to say that P and C defined as 1 over NCF over P minus CFP strongly contextual. This is just the non-contextual part. One thing that's probably a valid way of thinking about P non-contextual is that this is the best non-contextual approximation of P. So when we want to assign an operational interpretation to this number, this non-contextual fraction, we'll see maybe in the next lecture that the non-contextual fraction can be interpreted as bounding the ability in a particular computational model known as MBQC. It bounds the ability for an empirical model to compute a certain kind of function. So if the function is a Boolean function that's linear, then a non-contextual model can absolutely simulate it or compute that function deterministically. If it's nonlinear, when we're dealing with binary outcomes, that's important, then a non-contextual model cannot deterministically compute that function. And so, I mean, if you just want to use non-contextual resources, then this model will tell you the best approximation of computing that nonlinear function that you could get. So there's a way to sort of interpret this as the best non-contextual approximation, and then this actually can have an operational sort of meaning in terms of computing Boolean functions. Um, mhm. Okay, so I actually want to. So there's another interesting sort of related to this. I think that there is a sort of very interesting resource perspective that you could take on the contextual fraction or non-contextual fraction. So one, you know that, or you can think of CF slash NCF as quantifying the amount of contextuality. Okay, that's good. So you can sort of use this as a sort of numerical number telling you, okay, this empirical model has this much. Very nice. But the natural sort of corollary to this is then, well, which operations are contextuality non-increasing? So if I have some amount of contextuality in my empirical model, it's important to know what sorts of operations do not increase the amount of contextuality. So I think the best analogy that I could give here is to entanglement theory. So just without going into the full thing, we have maybe a monotone that assigns to things that are completely unentangled or separable, or the convex mixture thereof. We say that the amount of entanglement there is 0. Okay, very good. And as you increase the amount of entanglement, it should also, this monotone should also increase. Now then, what should we say does not increase entanglement? So you can sort of identify some natural operational procedures which should not do this, right? For example, you know, well, yeah, I think a natural example is just local operations. So if you have Alice and Bob, each of them has their own sort of, has their own qubit. Maybe the joint qubit, the full quantum state is a Bell state. And Alice and Bob are allowed to do local unitaries. We do not expect that local unitaries, they could do a lot of different things. They could be interesting from the point of view of quantum computation. We do not expect local unitaries to actually increase the amount of entanglement. So that would be an example of an operation that's entanglement non-increasing. Often we also talk about things like mixing, which will also appear in the contextuality resource theory. By mixing, I mean if I have two different empirical models, or rather in the entanglement picture, I have two different states and they have different amounts of entanglement, then doing their convex mixture also yields another quantum state and another amount of entanglement. And we usually think that this should not be as much as the maximum between the two of them. You've mixed, the initial states could have different amounts of entanglement, and we sort of have this intuition that mixing them should not increase that. It should definitely not be more than the maximum of the two of them, right? Another example would be classical communications. Classical communications are not going to be being classical in nature. They're not going to actually add to the amount of entanglement in your quantum state. Okay, so in contextuality, what are sort of the non-increasing operations? So I claim, so here are the so-called free operations. One, I mentioned before, we have probabilistic mixtures. I think that this is a fairly natural, I mean, we can show actually that these are, by the way, these are not assumptions. They come from the definition of our resource monotone, the contextuality fraction. But we will see that among the free operations are probabilistic mixtures. Another one, I'm following translation of measurements. So I'm following here Abramsky et al., where they sort of define very rigorously this non-contextual fraction. What is the translation of measurements? I tend to think of these as relabelings as a special case. Relabeling of measurements should certainly not increase the amount of contextuality. Another example that we'll see is if you have a contextuality, a measurement scenario that embeds, it goes into a different contextuality scenario, you would not expect that just seeing that coming from the bigger contextuality scenario to the smaller one is actually going to be contextuality increasing. You'll see that actually by the definition of the way that this translation of measurements works, you have to marginalize over something, and marginalization is throwing away information. We have the intuition that throwing away information should not increase the amount of resource that you have. I mean, that's the same thing with mixing. Mixing is, again, you're diluting the one of these two empirical models or one of these two quantum states has more entanglement than the other. Convex mixtures only dilute this. They don't increase it. So you have a translation of measurements to be defined. And this one's a little bit more intuitive. Coarse graining of outcomes. So I say that this is a little bit more intuitive because, again, coarse graining is immediate in that if you have a set of outcomes that includes a smaller set, then you go to from the bigger set of outcomes to the smaller set using, again, marginalization. Throwing away information should not increase the amount of contextuality. We'll give an example rather than actually proving these, because I think formulating it is a little bit tricky, but I think that there will be some representative examples that will give the flavor of it. Okay, so let's just start with mixing. This one is simple enough that I think we'll be able to just prove it very quickly. So we have a mixed empirical model, alpha p plus 1 minus alpha p prime. And alpha is, of course, between 0 and 1. And define this b vector. So we, in principle, there's a non-contextual fraction for p. There's a non-contextual fraction for p prime. So we define a feasible solution. So what do I mean? I should be a little bit more explicit. We know that p, one of these pieces here, can be written as let's be a little bit more specific. Let's say lambda hat or lambda star, we were using star for optimum, times, sorry. Sorry about that. Okay, let's do it like this. Plus 1 minus lambda star PSC. And of course, lambda star is coming from MB star. Oh my gosh, just totally messing stuff up right now. 1 transpose B star. Okay, so this is the optimum for P. We also have an optimum for P prime. Lambda prime star P prime and C plus 1 minus lambda prime star P C prime. And this is lambda prime star is equal to 1 B prime star. Okay, so we know for a fact, and we'll give a nice example of how this works, that when I plug in these decompositions for P and P prime, this will give also another value for, this will give a decomposition for P bar. How does that work? Well, we just plug in these decompositions. So P bar is equal to alpha times lambda star P and C plus, and I'll just use bar for 1 minus PSC plus alpha bar times lambda prime star P and C prime plus lambda, the corresponding 1 minus of that, P prime SC. And so you get something that looks a little like this. I'm just going to combine all the non-contextual pieces. So it's going to be alpha lambda star P and C plus alpha bar lambda, no, not bar, prime star P prime and C plus some other stuff. This will be combined into a non-contextual model. And so I have a decomposition for P bar here. This decomposition for P bar can be used to lower bound the maximum that you would expect for this. Because I found some solution, I know that the maximum is greater than that. So if you just know what the decompositions are for each of these, then you already have a lower bound for this one. In particular, yeah, I think you have to mess around with it just a little bit. But here you have alpha, here you have alpha prime. And then you can take out whichever one of these is bigger. I think there's a way to finagle this, but there's actually a more straightforward method. So the idea is going to be just define the following. So let me just go over here. You can define P bar to be equal to alpha times P star plus 1 minus alpha P prime star. So we know, for example, that M B bar is going to be equal to alpha M B star plus 1 minus alpha M B prime star. Well, I know that this thing is less than or equal to P, this thing is less than or equal to P prime. So I know that this thing is less than or equal to V P bar. I could make it a little bit more explicit. This thing is going to be less than or equal to alpha P, less than or equal to alpha P plus 1 minus alpha, and this part is less than or equal to P prime, which is, of course, less than or equal to, maybe I didn't keep the same notation, but we're thinking of these as vectors, and this is going to be less than or equal to P bar. So what that means is I start with this thing, I just define it, but I see that the coefficients of these must be non-negative because the alphas are non-negative and the b's are non-negative. Everything is non-negative, and it satisfies that MB is less than or equal to P. So this is a possible solution, and so we know that this thing, we know that this implies that 1 B bar is less than or equal to the non-contextual fraction of P bar. It's feasible, it's a possible solution, but we haven't done the optimization yet, so all we can say is that this thing is less than or equal to. And in general, what we actually want to say is the following. I'm all over the place. So in general, so what you have is 1 B is equal to alpha times this right here. So we know that it's feasible. Now we plug this back in to the objective function. So we have alpha times 1 B star plus 1 minus alpha 1 B prime star, which is equal to alpha times, this is the non-contextual fraction for P, plus 1 minus alpha, the non-contextual fraction for P prime. But we know that this is not necessarily the optimum. So this implies that 1 bar equals alpha NCF plus 1 minus alpha NCF prime is less than or equal to the NCF of P bar. I hope that was clear. The idea is just that you know that if I have a mixture, I can define a mixture of B's in terms of the optimal solution for each. And that leads you to have a new decomposition. That new decomposition cannot be greater than, just because you haven't done the optimization yet. You have a feasible solution, so you know all you can say is that this is less than or equal to, because the optimization is for the maximum. Okay, so we'll continue in a second. So with regards to mixing, I did want to do a little example just to illustrate the point. So imagine that you have an empirical model, which is maybe as classical as you could hope for in the following sense. So imagine the CHSH scenario, and you have a set of boxes that I'll describe like this, where the mu box is just all 1/4. So why do I say that this is classical? How do I know that? Any box like this, I could imagine just flipping coins at random. So there's only classical randomness at play in order to describe a box like this. Nevertheless, it is possible to describe this thing in the following way. So imagine that I have some PPR. So this is a PR box. I'm going to describe this as plus, 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 minus, and P prime PR is equal to minus, 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 plus, and I will say what these plus and minuses are. So plus is going to be the perfectly correlated box, 1/2, 0, 0, 1/2, whereas minus is the perfectly anti-correlated box, 0, 1/2, 1/2, 0. So these are both going to be PR boxes. This one we've seen is strongly contextual. This one is also strongly contextual, but we haven't looked at it specifically before, I don't think. But what you can see is that this completely random state here, P, can be written as 1/2 P PR plus 1/2 P PR prime. Why? Because if I take a 1/2 with one of these pluses, I get 1/4, 1/4. And if I mix it with a minus, I get 1/4, 1/4 on the off diagonal. So I get precisely my P. Now these are both strongly contextual. So is it true that the contextual fraction of P is equal to 1? No, I just described a hidden variable model. In fact, I can write it out in terms of our deterministic empirical models. I won't write it down right now, but so what I want to emphasize with this is precisely that you haven't done the optimization here. So you haven't done this optimization. You found a decomposition in terms of strongly contextual things, but this is not the entire picture. So all you can do here is say that the contextual fraction is at most 1 because you found such a decomposition, but you could find better decompositions. Essentially just you will find that almost any support is possible here, and then you can start finding lower bounds on the non-contextual fraction. Which is just to say that it is important to keep in mind that finding a decomposition does not necessarily tell you what the contextual fraction is. It just tells you that you can bound it. So in this case, we found a decomposition where the contextual fraction is 1. So the non-contextual fraction is at most 1, and the contextual fraction is at most 1, non-contextual fractions at least 0. But if I write down something like P is equal to 1/4 times the box that has 1s all in the top left corner, plus 3/4 times something that's left over from that, then, and this is possible, in fact, I can take out this distribution here, and I will be left with another one where there's 3/4 everywhere, or sorry, yes, it is possible to write it like this. And then now I will have said, once I find this decomposition, that means that the non-contextual fraction, because now I have a quarter weight that I've pulled out, that means that the non-contextual fraction of P is greater than or equal to 1/4. And if I'm able to keep doing this, then I can keep increasing the lower bound on this. I mean, the way that I'm describing it is not really an efficient way to do it, but in some simple cases like this one, you will be able to probably come close to finding the non-contextual fraction just by finding some supports and keep pulling them out until the total weight of the non-contextual part is precisely 1. So I want to go to some of our other examples. So now we have that second part, which is what I called the translation of okay. So it's going to be good to start with an intuition here. So the idea is that, so let's give an example. The example is as follows. Suppose I have 2 measurements and my set of contexts are just the most basic one you could think of, x and y. I can think of this as being somehow like a line, x, y, and the fact that they're in a context means that I draw a line between them. Now imagine that I have another measurement scenario, x prime, y prime, z prime, all filled in. What filled in means is that I'm going to have a context with all 3 of them. So there's going to be an outcome over all 3 measurements. So in this set, we have x prime equals x prime, y prime, z prime. And I have my set of contexts, just a single context, x prime, y prime, z prime. So that means that they're jointly measurable, and I can get an outcome for all of them at the same time. Now, when I think of a translation of measurements, what I want to think about is a function f that maps me to another measurement in the other set. So in this case, I map x to x prime, y to y prime, in such a way that if this is a context, then x prime and y prime are also part of the same context. Whenever wherever they're mapped to, they should always be in a context together if they were in a context in the original one. So what this allows me to do, so I have some function f, which tells me how to go from this original set to this one. Now, suppose I started with an empirical model here. This means that in this case, I just have one single probability distribution. I can define an empirical model. So if I have an empirical model P prime here, I say that I can define an empirical model F star P prime according to what? Well, I just will marginalize over my additional measurement. So here I have P prime, I have a outcome over X, Y, and Z. I marginalize over Z prime, and I get a distribution over this. The map is defined by marginalizing over these additional measurements. So there's a way to make this all, much more formal, but the basic idea is that maybe I can just write it like this. Suppose we have two measurement scenarios. It will help maybe to go up here, actually. So suppose we have two measurement scenarios. M is X, O, and C, and M prime is X prime, O, and C prime. And now what I want to do is define a function or a map from X to X prime such that if C is a context in C in the set of context for M, then we have that f of C, just basically what do I mean by this? I take every element here, that's like taking the x and y over there, and I say that they are the subset, a subset of some C prime that's in curly C prime. That would be the equivalent of this triangle. For every C in C prime. You can think of this as an inclusion. And then, so the idea is that, I mean, just the more formal sort of idea is that if I have an empirical for an empirical model P prime on M prime, then we can define F star P prime on M. Abramsky, they call this a pullback. And the idea is that you define this thing by F star P prime of C. Now this notation is going to get a little not so nice here, so we have the joint outcomes on F of C such that TF restricts to S. I didn't do the full thing. Star P prime C of S. P of F of C of T. Okay, I think that this is a little bit of a, we need to unpack this a little bit, but the idea is that we want to eventually end up with a empirical model on M. And in M, our measurements are in X and our contexts are in C. Whereas in M prime, we have more measurements. The context could have additional measurements in each of them. So ultimately, what this whole expression is trying to do for us is to just marginalize over, as we did here, these additional measurements so that you get something that's only on C. When you do things in this way, the basic idea is, again, because you've just done the marginalization, you can be a little bit more precise here, but it takes some work. The ultimate idea, though, is that the non-contextual fraction of this guy, so if the original one was P prime, sorry, it goes in this direction. So the new one has greater than or equal to non-contextual fraction to the original, which was p prime. The way to show this, if we just take a second more, is to suppose that that b prime gives the optimum for p prime, gives the optimum non-contextual fraction, and then you define C yeah, it's a little bit tricky to write down, but the idea will be to write down, this is a B, B will be written as, C will be written as the sum over, maybe a little bit easier to say like this. Okay. C of G, G prime in O of X prime. So we sum over all global outcome assignments in X prime. So we're doing the marginalization such that G prime restricted to X equals G. All over, not such that B of G prime. In words, we're summing over all joint assignments in the larger set of measurements, X prime, such that we're going to sum over all of them. And then in particular, we are, no, there's no double sum. Okay, no, the original one was correct. So we're summing over all global outcome assignments. Here we have C of G. This is the weight according to the Gth global outcome assignment in X. Now we're summing over all those in X prime in the M prime measurement scenario such that they restrict to G. So you're doing a marginalization, and because of this, you will get that 1 transpose C will actually be okay, so the 1 transpose C actually, when you work it out, actually equals the non-contextual fraction for P prime. So because we've written down a feasible solution, we know that our non-contextual fraction is at least this size or this amount. Yeah, that was a little bit of a confusing sort of argument, but the idea is, again, I can just define something. I defined something. I didn't show that this is a feasible solution, but it is. And once you show that this is a feasible solution, compute its objective function, and you know that the non-contextual fraction for this new one will be at least that amount. So you do get that NCF P prime is less than or equal to NCF of F star P prime. Okay, so I think an example is in order here. So let's see which way to go. Let's actually, perhaps we can just get rid of the. Okay, so an example is in order here. So we have this, let's say x, y, and our function f takes us such that x is mapped to x0, y is mapped to y0, y1, y0, x1. So this is the CHSH scenario. How do I see that? I have 4 different types of measurements, Alice's measurements, Bob's measurements, and each context is a line between one of these. And I'm taking y to go here, x to go here. So suppose, for example, that I have an empirical model, which is a PR box, plus, 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 minus. I've mapped y to y0, x to x0. So when I want to do this other map, f star, which takes p to the new empirical model defined from p, what do I have to do? Well, the idea will be, first of all, these contexts don't exist over here because I've only sent x to x0, y to y0. These other ones are not there. So I only have a single context. It's corresponding to this plus. And this plus is just, this is just one table of numbers, 1/2, 0, 0, 1/2. This thing is classical. So what I saw was that I had a non-contextual fraction of p equals to 0. And here, the non-contextual fraction of f star p is actually equal to 1. And what did we say? That the non-contextual fraction for the original empirical model has to be less than or equal to the one that I map it to, like this. So here you see a sort of concrete example of how this is working. The basic idea is, when you go from here to here, you're throwing away a bunch of information about these contexts, and these are precisely the additional correlations you need to get that where the contextuality becomes present. So I think that we will conclude with maybe another example would be a good idea. So how about okay, so coarse graining. We are going to have a measurement scenario. Maybe it'll be easier. It'll be the same as the CHSH scenario. But unlike our other times of looking at the CHSH scenario, we're going to have 3 outcomes. x1, y0, but here now outcomes are 0, 1, 2. And I'll define this as z mod 3. Basically, the integers modulo 3, so that, when I go to 4, it's actually 1. When I go to 5, it's actually 2, so on and so forth. So imagine that you have this empirical model with the 3 outcomes. So I have to give myself a little bit more room, but the idea is going to be I have 1/3 along the diagonals. This is very reminiscent of the PR box. And then I have some weirdness going on. 1/3, 1/3, 1/3, and everywhere else is 0. I don't want to put them all in, but you see that these are diagonals. And then here I will help to make it explicit. Indeed. Now imagine that you did the following sort of maneuver. Let's see if maybe... let's say that we did a map F, or let's define it as something. H goes from Z3 to Z2, which takes 0 to 0, 1 to 1, and 2 to 0. Basically, I'm taking the elements of this and setting them equal to their modulo 2 equivalent. So I have the only extra element here is 2, and I'm sending it to 0. So what is that going to do here? Here I have the outcome. Alice has 0, 1, 2, 0, 1, 2. And I do that for all the different boxes. So how am I going to do the marginalization? I'm basically going to identify anytime Alice or Bob has an outcome that's 2, it's going to be added with when they get the 0 outcome. So how's that going to work? Here, for example, so let's call this distribution Q. Basically, anytime I see a 2, these are going to get mapped to a 0. So I'm going to add up so when I say what is the probability for Alice to get 0, 0, well, it's the probability for Alice to get 0, 0 here, plus the probability for Alice and Bob also to get 2, 2. So this will be 1/3 plus 1/3, 2/3, 0, 0, 1/3. Now I'm just getting rid of the last column and in row in each box, and I'm going to add up this 1/3 with this one. So this is a coarse graining. I'm binning together different types of outcomes. I'm binning together the 0 and 2 outcome and adding their respective probabilities. So here I will get the same thing. 2/3, 0, 0, 1/3. I will do the same thing here. 2/3, 0, 0, 1/3. And then finally, this one's a little bit trickier. 0, 0 stays the same. And then normally, if I had added 1 and 1 together, sorry, no, this would stay 1, 1. This would be 2, 2. That would normally go to being identified with 0, 0. This is the 0, 2 outcome. The 0, 2 gets mapped to 0, 0, but there's 0 here. There's also the 2, 0 outcome, which is 1/3. So I get a 1/3 here. Okay, now I have to look at the 0, 1. 0, 1, I get 1/3. And then I have to look, so for the 0, 1, what could map to 0, 1? Or rather the other way around. What maps to 0, 1? could be 2, 1, or 0, 1. So 0, 1 is 1/3, and then you also have 2, 1, which is 0. So this one is 1/3. Similarly, we have 1, 0. What maps to 1, 0? What maps to 1, 0 is 1, 2, and 1, 0. So where's 1, 2? That's right here. That's Alice gets outcome 1, Bob gets outcome 2. So this is 1/3. And then 1, 0 is 0, so this is 1/3. And then finally, we have 1, 1. And the only way for 1, 1 to happen is the same in both, so 1, 1. So that's 0. So this is our new table. And now we have to ask here, it turns out to be the case that, so let's continue over here. It turns out to be the case that the non-contextual fraction, and you'll do this in the homework, of p is equal to 0. Precisely because this is sort of like a PR box, but with 3 outcomes. So you'll have to take my word for it. The non-contextual fraction here is 0. Now what about this? Now this thing looks very much like a PR box. In fact, we can write down Q is equal to 1/3. Let's see. No, sorry. Yes, 1/3 times a particular box, the one with all ones in the top left corner, plus 2/3 times PR. So we know, because I've been able to pull out a weight of 1/3 here, I know that the non-contextual fraction of Q is at least 1/3. It's at least 1/3. And so we have that NCF of P equals 0 is less than or equal to 1/3. 1/3 is the value I got from this decomposition, just from, and by the way, this is going to be optimal, right? Because I found a decomposition and it's now, I believe that, I'm actually not sure if it's optimal. You would have to actually run it in the computer program, but it looks optimal to me because I pulled out this weight of 1/3. What's left over is strongly contextual. There's nothing left, no classical deterministic outcomes to subtract from here. So I believe that this is optimal. But just to be safe, NCF of Q. Again, you have that the map from here to here, which includes basically marginalizing over equivalent outcomes, is going to just increase the amount of non-contextuality that I have, therefore decrease the amount of contextuality that I have.